Illustration of longest common substring. In the last lecture, we learned about longest common substring problem. We learned how to solve this problem. What is the algorithm to be followed to solve this problem? Here, what we are going to do is, we'll see how is the dynamic programming table getting filled while you're solving this problem. When you're actually running this algorithm, what is the order in which the computer is filling this table and how exactly is this filling each table, each entry in the table. Once you understand this, the concept of this algorithm, the idea of this algorithm will be very clear for you. So this is the aim of this lecture. We'll go through an example. We'll take two strings and using those strings, we'll illustrate how is this table getting filled. Let us look at the algorithm that we learned in the last lecture. What did we learn about the longest common substring problem? There will be two strings S1 and S2 and we want to find the longest common substring that is common to S1 and S2. What is the algorithm that we learned? First step we learned we want to have a DP table. There should be a two-dimensional DP table which is of length size m plus 1 cross n plus 1. What is m and n here? M is the size of your first string, let us say x, and n is the size of your second string, let us say y. So I'll note it down here so that you won't have any confusion. X and y are the strings that you're having. X is having size m, that is length m, and y is a string which is having size n. So you are having a DP table which is of size m plus 1 cross n plus 1. What does each entry in this DP table represent? dpij, that is each entry in the DP table, it will represent the length of the longest common suffix of x considering all the letters till the ith letter and y considering all the letters till the jth letter. So for jth letter, why am I writing j minus 1? Because it is 0 indexed. So the first letter is at index 0. So at this point, at dpij, you are considering all the letters in x till the ith letter and all the letters in y till the jth letter, and you will be considering the longest common suffix length. That is what you will mention in dpij. What is the next step? We already learned that the second step is to initialize your DP table. Your first row and first column, both of these have to be initialized to all zeros. In the first row and first column, you will have all zeros. What is the next step? In the third step, the most important step, you have to iterate through all the entries in X and Y. How do you iterate? While iterating, for any particular combination of a letter in X and a letter in Y, you'll check whether both those are equal. While checking, if it turns out that xi minus 1 is equal to yj minus 1, in this case what will you do? In case the letters are equal, then we learned that your new entry dpij, this will be equal to whatever you found as the longest common suffix considering letters till I minus 1 and j minus 1. So dp of I minus 1, j minus 1 plus 1. So whatever you got as the answer by considering all the letters previous to this plus 1. Why is this plus 1? Because the present letters are matching. So the length increased by 1. What is the other case? Else case. In case these are not matching, then dp of ij, what did we learn? This should be equal to 0 because substring should always be contiguous, because of which if it is not matching, it is not possible to have a common substring. So the length of common substring is 0. So this is the algorithm. What is the last step? Once you complete this, you have to see whichever is the maximum value in your complete DP table. That is the length of your longest common substring. This is the algorithm. What we'll do, let us take two strings and using these two strings, we'll understand very clearly How is this algorithm working? First string, let us say our two strings are x, which is equal to underdog. Underdog is a string, and we'll take one more string, let us say render. So that we'll have render in the vertical axis, we'll take render first. This is according to the algorithm what we had learned. Render is our first string. What is a second string? It is underdog. We want to find the longest common substring. Underdog is our second string. Our task is to find which is the longest common substring among the words render and underdog. What do you want to do? You want to construct a DP table. How do you construct DP table? You will have underdog in this axis. UNDER DOG. This is in one axis. First entry is for 0. And what about the other axis? You will have the letter word and render. So it will be R. First it will be 0. Then R, E, N, D. This should be D, E, R. We'll draw the table here. This is the table. We want to complete this full table. Once you complete the table, you will have all the entries. We are going to see how this table can be completed. Once you understand this process, that is exactly how each entry is filled here, the algorithm will be very clear for you. You won't have any confusions hereafter about how is this algorithm working. This is what you want. So that's why we are having special lecture for this. Let us start filling this table. In the table, what is the first entry? First thing, we'll just follow the algorithm as it is. That's easier. So first thing is to have a 2D table, which is of size m plus 1 cross n plus 1. You already have that. This is your DP table. What is the next step? Next step is to make the first row and first column as all zeros. How will you make first row and first column as all zeros? Your first row, this will be having all zeros. What does this signify? This signify that whatever be the length of your second string, which is underdog, if your first string is of length 0, we are only considering 0 length at this point. If your first string is of length 0, then it cannot have a common substring at all because it is not having anything in it, because of which all the entries corresponding to it will be 0. The same way, if your second string underdog becomes of length 0, that is what the first column denotes. Here it is length 0. It is not an O, it is about length 0. All these entries will be 0. Render. Now we are going to start filling the actual entries. That is those entries which may not be 0. Those entries are what are important. What is the procedure to be followed? For each entry, what are we going to do? If xi minus 1 equal to yj minus 1, that is, if the ith entry in x is equal to the jth entry in y, if those letters in the strings match, then what will you do? You will take diagonally above element, whichever is the element present on the diagonally top position. That is what you will consider. To that you will be adding 1. What is the speciality of this position? This position tells you dp I minus 1 j minus 1. That is, if you consider all the elements till the I minus 1th element in x and j minus 1th element in y, then what is the longest common substring? That is what it says. Not just substring, the suffix. Why we not need the suffix itself here? Because it considers this last letter specifically. Then only it can be a suffix. So using this logic, we are going to fill. One more thing I'll do is, I'll number these letters so that it will be easier for you to match these. Underdog and render. So in render, you have 0, 1, 2, 3, 4 and 5. And in underdog, 2, 3, 4, 5, 6, 7, 8. You have 0, 1, 2, 3, 4, 5, 6 and 7. So index is still 7, which means 8 letters here. You have 6 letters here. Let us start filling this table. Keep in mind that filling this table, if you already understood the longest common subsequence algorithm that we discussed in previous lectures, This will be way easier because the procedure is almost same and it is easier. It is a simpler procedure comparatively. Let us start filling this. While filling this one, first one, what should be the consideration? According to the algorithm, you have to see whether ith letter in x is equal to jth letter in y. That is, if xi minus 1 is equal to yj minus 1. If it is, you have to add 1 to the value in the diagonally above element, top diagonal element. Let us see the entries. Here r and u are the ones corresponding here. R and u are not equal, which means what should you do? Whenever it is not equal, you should directly write 0. This is the logic. Whenever it is not equal, what should you do? You should directly write 0 here. This should be 0. Here n and r are not equal, so it is 0. D and R are not equal, it should be 0. E and R are not equal, it should be 0. R and R are equal. If it is equal, what should you do? Whatever is the value in the diagonally above element, this one, to that you should add 1. So when you add 1, the value will be 1 here. 0 plus 1 is 1. Next one is R and D. They are not equal, so you don't have to see anything else, directly put 0. This is why this algorithm is easy. R and O are not matching, 0. Again 0. What about the next row? E and U are not matching, it is 0. N and E are not matching, it is 0. Next thing, E and D, they are also not matching, it is 0. Here comes E and E, they are matching. What should you do now? You should see whatever is in the I minus 1, j minus 1 element. If this is dij, then what is there in di minus 1, j minus 1? The answer is 0. So that plus 1 will give you 1. What about E and R? They are not equal, so it should be 0. Same reason, all these will be 0. Next row, if you consider, you have N and U to begin with. N and U are different, so this should be 0. N and N are matching. What should you do? You should see the element diagonally above it. To that, you should be adding 1. So you will get 1 here. N and D are not matching. N and E are not matching. N and R are not matching. The same way, all these are zeros. Next row. This row, you have D on one side. So D and U are not matching. D and N are not matching. D and D are matching. What should you do when it is matching? See whatever is present in the element diagonally above it. So here 1 is present. What should you do now? To that 1, you should add 1. So 1 plus 1 will be 2. 2 will be your entry here. D and E are not matching. D and R are not matching. Again, D and D are matching. Whenever it is matching, see the element diagonally above it and then add 1 to it. So 0 plus 1 is 1. Again, D and O are not matching. D and G are not matching. Let us see the next row. In the next row, you want the top element. E and U are not matching. E and N are not matching. E and D are also not matching. What about E and E? They are matching. So you should see the diagonally above element. To that is the value 2, you should add 1. So it will be 2 plus 1, 3 here. E and R not matching. E and D not matching. The same reason, all these are zeros. What about the last row? In the last row, R is on one side. R and U not matching. R and N not matching. R and D not matching. R and E not matching. R and R matching. What should you do? You should see the element diagonally above it and add 1 to it. So 3 plus 1 is 4. What about this one? R and D are not matching. R and O not matching. R and G again not matching. Now your complete DP table is filled. What should you see now? Whichever is the maximum value present in this complete DP table. This is not like the longest common subsequence algorithm. We had seen the last entry of the DP table, but here you have to see whichever is the largest entry present in the DP table, wherever it be. So in this particular case, you can see the largest entry is present here. 4 is the largest entry. You understood that the length of longest common subsequence is 4. Why is it 4? Because the largest entry is the length of longest common subsequence. You know the length of LCS. LCS length is equal to 4. Next question is, what is the actual LCS? It is of length 4, but what is it? What exactly is this common substring? In order to identify that, you have two ways. Because it is a common substring, you can take it either from Underdog or from Render. Both of the strings are having this. How will you find out? I told you in the last lecture that whenever you have a particular value that is largest, you should always keep track of the index at which you found it. You have to keep track of any index, that is either of the string X or of the string Y. That is your choice. Consider that you had kept track of index of Underdog. In that case, the index of R will be what you get as the answer. If you get the index of R, then you know the length is 4 and the last letter is R. So you have to backtrack from here for 4 letters. So N, D, E, R, this is the largest substring. Other case, if you kept track of the other string, that is render, you know R is the index that you are keeping track of. That is the last letter. Wherever you find the maximum value, that will be the last letter of that substring. Moreover, you know the length of that substring is 4. If you know the last letter is this and the length is some particular number, then you can just take those many letters going backwards and that will be a common substring. What will be the common substring here? R is one letter, go backwards E, D and N. So now you can write N, D, E, R. This is the longest common substring. What is the answer here? The actual LCS in this problem is N, D, E, R. If you check, the same N, D, E, R is present in Underdog. It is also present in case of Render. So this is how you find out the longest common substring. In the next lecture, what we'll do is, instead of filling this complete DP table, there is a trick. You need not use this complete space. The space used here is, what is the total space complexity? Space complexity is order of m into n, and this is because of the dynamic programming table. If you look again and if you think a bit more, you will understand that you actually don't need to use this whole table. The reason is, which entries of this table are you using? You are not using all the entries at all points. The only entry that you need is the one diagonally above it. For any particular element, you only want the element diagonally above it, which means the row just above it is the only row of significance. Using this logic, what can we do? Instead of this table, we can simply use an array and try to solve the same problem. This is what we'll do in next lecture. We'll try to decrease the space complexity. Time complexity will remain the same because you have to go through both strings. Space complexity can be reduced. Let us see in the next lecture how is it reduced.